So we've been talking about how software engineering is a really difficult problem and how people use process level metrics, software development process level metrics to quantify the quality of software and how that is inadequate. We also talked about how even if you get the best process, it still doesn't meet the requirements of mission critical software. Software where there's a large amount of investment involved, or software which involves operations which can potentially involve loss of life and things like that. So here's an example of a critical application. There's this famous example where the Ariane 5 launcher had an overflow problem. I think it was a buffer overflow problem, and the estimated cost of the overflow was $500 million. Just the direct cost, and if you include the indirect costs such as delays and lost markets, etc., it was over $2 billion of loss at that time. And the question is, when something bad like this happens, whose responsibility is it? And for much of the software that we use, it actually comes with no warranty. So here is an example license that I pulled out. It says that except when otherwise stated in writing, the copyright holders and or other parties provide the program as is without warranty of any kind, ... Or here's another clause which says, in no event unless required by applicable law or agreed to in writing will any copyright holder be liable to you for damages including any general, special, incidental or consequential damages arising out of the use or inability to use the program, etc. So, such important applications rely on software, and yet there is no way to pin, or for most of the software, there's no way to pin responsibility or blame on anybody, because these software are basically coming with licenses which don't really give you any kind of guarantees. And the reason these software basically come with no guarantees is because they all know, the developers know, that it's too difficult to basically be able to certify that the software is correct and to take financial liability under that kind of guarantee, and nobody wants to take such a guarantee, and that's one of the, that's the current state of affairs, but clearly this state of affairs is not an ideal state of affairs, and it needs to change, because if we want software to be present in critical applications which may involve all the kind of things that we've discussed earlier. There's also this famous example of an X-ray machine or some kind of radiation machine that had a race condition, and because of which it exposed the patients to higher levels of radiation, and it was only after a lot of different patients had gone through such bugs and kind of had started seeing adverse health effects including death, that people realized that it was basically because of race condition in that medical instrument. And so these kind of things are kind of really sad when they happen, and clearly there need to be better obligations and liability pinning for these kind of settings. And so what you really want is, and this is, by the way, a very long-standing problem. It's not a problem that has emerged in the last 10 years or last 20 years. Ever since people started talking about software, right from 1960s, 70s, 80s, people have talked about how we need to basically have guaranteed safety and security of software. And I call that a moonshot goal, because it is indeed one of the most important goals in this, one of the most important problems in the computer science. And if we look at where we are, we're basically making improvements, we're making progress towards this goal step by step. For example, there are algorithms such as the ones that we're going to discuss in this course based on abstract interpretation, which check the absence of large categories of bugs. Then there are techniques that improve the precision and the scale of such techniques. And then there are techniques that automate these kind of analyses, so that there's minimum human effort that's required to do these things. And so as we are kind of climbing this ladder, hopefully we are eventually, at least to some degree, be able to provide safe and secure software, at least for our critical applications, if not for all applications. In fact, this has been also articulated as a grand challenge in computer science by Tony Hoare in 2003. Tony Hoare is the scientist behind Hoare logic, for example. And in the Journal of ACM, he said, the construction and application of a verifying compiler that guarantees the correctness of a program before running it is a grand challenge in computer science. Currently, the compiler is basically involved in getting the program into a form such that it becomes executable. But also, if it can guarantee the correctness of a program, that would be a great thing. And of course, I should point out here that the problem itself is underspecified in this sentence, because when you say correctness of a program, guaranteeing the correctness of a program, you also need to define what is the correctness of a program, right? So yeah, but after you do that, even then, it's a pretty hard problem to solve. So let's get into some of the technical material required to basically move towards this goal of safe and secure software. One of the concepts, mathematical concepts, is the concept of an assertion, right? What is an assertion? Assertion is a statement, or statement is just another word for logical predicate, which basically says what should be the values of the program at a particular execution point, for example, and says an assertion is a statement about the values of the program variables at some program execution point. And it's not necessary that the assertion should always be true, or it may be possible that the assertion is always false, or it's possible that assertion is sometimes false, etc. So here's an example of an assertion. You can say, at this point x is equal to 0, and that's an assertion. Or you could have the same assertion specified in some kind of higher level logic. For example, you could say for all x, where x is some kind of, let's say, integer, there exists a y, so where x and y are both integers, m1 at address x is equal to m2 at address y. Where m1 and m2 are basically memory states, and x and y are basically indexing into the memory as addresses. And so, there can be all kinds of assertions. I'm using these two examples just to show the different types of logical statements that you can construct to form an assertion. Further, there are two special types of assertions, and we give them a name: the precondition and the postcondition. So for a given program, a precondition is an assertion at the program entry. So these are, this is what we can assert at the program entry, and that's called the precondition. And postcondition is an assertion at the program exit. So for example, if the program is y equals x star 2, and let's say the precondition is x is greater than 0. So the precondition is being guaranteed by somebody who is calling this program. So anybody who kind of wants to invoke this program has to basically ensure that x is greater than 0, and that's what precondition means. And then when you execute this, the postcondition says what are the some assertions that will hold for this program at this particular point, which is at the program exit. So let's assume that the program was only a single statement. Then after this single statement is executed, well, here is one postcondition, which is x is greater than 0 and y is even. So y mod 2 equals 0 and y equals 2 star x. Right? This could be one assertion. You could create any kind of assertion. For example, you could just have said y is greater than 0 and y is even, and that would also be a valid postcondition. Of course, the first postcondition that I have is stronger than the second postcondition because it kind of specifies more properties, strictly more properties than the second one. The point is that any kind of statement on the program variables at a program point qualifies as an assertion. Now that we understand what an assertion is and what a precondition and a postcondition is, we're going to introduce the idea of partial correctness. So what is partial correctness? Here is a statement. If precondition P holds on the entry of a program C and program execution terminates, which means the C program execution terminates, then postcondition Q holds, right? And so if and when execution of C terminates. So this is also written in this syntax. Curly braces P represents the precondition, then the program executes, and then Q is again written in curly braces, which basically indicates the postcondition. And this is also called the Hoare triple notation, but basically it means that if P holds at program entry and C is executed, then Q holds. There's one more catch here: if and when C terminates. So if C never terminates, then this basically you don't, then you can say anything about Q, because it basically means that C should, we don't really know. So basically this is vacuously true. If C doesn't terminate, then PCQ is vacuously true, because if you notice, This says if precondition holds on entry and program execution terminates, then postcondition queue holds. But if program execution does not terminate, then the partial correctness says okay, then this is anyway partially correct. So if the program does not terminate, then this PCQ is always true, because if C is kind of non-terminating, then then this statement, basically the antecedent of the statement program execution terminates, is false, and so this whole statement would evaluate to true. So let's take some examples of 4 triples. Irrespective of the program, for any precondition, I can always say that true holds after that. So this is a tautology. So these are some tautologies that I'm listing on this slide. What is a tautology? That holds for every program and every precondition and every postcondition if it's being used. So if I start with any precondition, it could be this precondition could be true, could be something else, could be x equals 0. Execute any program, I would always be able to prove PC true, because if P is true and C terminates, then true holds, and true is anyway holds anyway. So irrespective of whether program terminates or whether P holds in the beginning of the program, true is always true, and so this is a tautology. All right, so this is a tautology. Similarly, this is a tautology, false CQ, because if at the program beginning the precondition is false, which basically means that this program is not reached, then C terminates, then Q definitely holds. So this is also something which happens to be a tautology, because if the program is never started and the program terminates, which is also basically means that the antecedent becomes false, right? So if you recall the partial correctness statement, it says if P holds and C terminates. So if P holds, which means if false holds. False can never hold, so the antecedent becomes false, and so the whole statement becomes true. The implication statement becomes true. So both of these are tautologies. Here's another example. Let's say the program was non-terminating. Once again, it's a special case. Let's say C was non-terminating. Then irrespective of what the precondition is, you can this statement is always true. This partial correctness statement that is denoted through a whole triple is always true. PC false, because once again the antecedent is false because C doesn't terminate. So you can prove anything, and which means you can prove false. In fact, because by the same logic, you can prove any other predicate Q. If you can prove false, then you can also prove anything else. So if P, for any precondition P, if C does not terminate and you execute C, and then PCQ holds. In other words, whenever C terminates, Q holds, but we know that C never terminates, and so basically we can always say that whenever C terminates, Q holds for any Q, right? And including Q equals false. And similarly, for example, you could say true, C false. For example, you could take true as if you start executing C and you say if C terminates, then false holds, because we know that C doesn't terminate, because we are basically assuming that this is a non-terminating program C. Here are some more examples. So let's say C was this program which says y equals 2 star x, the same kind of program that we used earlier. So if my precondition is true, which means there are no constraints on the precondition, x could be anything, for example, then when you execute this program, then you get y to be an even value. So y mod 2 equals 0. And so this is a valid whole triple. Right? So this is basically a statement of partial correctness in the sense that this specifies some kind of property of C. Similarly, you could say, if the precondition is x equals 0 and you execute C and C terminates, by the way, C will always terminate in this case because it's just a single statement, then at the end of the programs y equals 0. Of course, I should point out that these may seem very trivial, but I have kind of underspecified the problem a little bit. For example, I haven't specified what is the representation, what is the kind of range of x. Is it a bit vector? Is it an integer? Is it a floating point number, etc.? Similarly, I haven't specified what's the meaning of star. For example, if it's a bit vector, then star means something different from if it were an integer, and so on. But so I'm just kind of using some loose semantics here. Let's assume that x and y are integers, and so even then these kind of things hold. Even if you assume x and y are bit vectors, then also by and large most of these things should hold, except when you have to worry about kind of overflows and things like that in that case. the point is that when I specify C, I should also specify the semantics of C precisely. And I'm kind of not doing that discussion in its full glory. I'm just kind of using some syntax and using the common meaning of that syntax. For this discussion, you can assume that x and y are integers, and star is basically integer multiplication. All right, here's another whole triple. If x is less than 10 in the beginning, then at the end, at exit, you can be sure that y is less than 20. Or you could say if x is less than 10, then at the end you can be sure that y is even. Well, y is even irrespective of what x is, but if it's integer, but also when x is less than 10. Then. So all these whole triples are actually valid whole triples in the sense that they basically represent the partial correctness condition of C. They all represent different properties of C, some being more precise than others, but all of them are valid statements. Here's another example. So let's say C was an program with a loop, just like the kind of loops we have in the C language. And so you initialize a variable sum to 0, and then you iterate from I equals 0 to n. N is an input parameter, let's say, input argument, and I plus plus, sum plus equals I, and let's say you return sum at the end. And so here is a whole triple that describes, that is valid for this particular program. The whole triple is irrespective of what you start with. So the precondition is true. If you execute the program and the program terminates, by the way, in this program, you can basically assuming that n is a positive integer, or even if n was a negative integer, this program, you can argue that this program terminates, and assuming n is finite. And so you can say that, okay, so, if it terminates, basically evaluates to true because, it always terminates. Then sum equals n into n minus 1 by 2. Now, this is another kind of postcondition that you can infer. Of course, this is a more complex postcondition than the kind of examples that we have used earlier. In general, identifying the correct postcondition may be a pretty hard problem and can be undecidable, especially in the presence of loops. But we kind of try to do the best effort. And that's one of the reasons, this undecidability of identifying the appropriate assertion is basically one of the reasons why safety and security of writing safe and secure, provably safe and secure software is such a hard problem, and it's kind of called a grand challenge in computer science. Now, the last thing I want to point out is that assertion that holds is also kind of an abstraction. In our last module, we talked about how an abstract interpretation program basically says, okay, these are all the possible behaviors of the program, and then we basically put an envelope over that possible behavior and reason about the envelope and say, oh, this envelope of this possible behaviors cannot cause any unsafe behavior. And so because the envelope cannot cause an unsafe behavior, the program cannot cause any unsafe behavior because the envelope is an over approximation, an extra, it only kind of adds more behaviors, it doesn't subtract any behaviors. And so an assertion is nothing but an abstraction because, it's an envelope. An abstraction is just nothing but an envelope. It can be a precise abstraction, which means it exactly defines all the possible behaviors, or it could be a loose abstraction, which means it adds few more behaviors. So, for example, if the possible behavior of the program were that y can take some values 2, 6, 8, 10, blah blah blah. Notice that I have deliberately omitted 4 here. You could basically say, assertion could be y is greater than 0 and y is even. Now this adds more behaviors than the actual program behaviors. For example, it also accepts 4, but that's why we call it an abstraction, because it may add more behaviors, but it should not remove any behaviors. So if in all these values that y can take, I'm sure that y is always greater than 0 and y is always even, then this is a valid assertion, and it also serves as an abstraction.